The invitation. Thanks for having me come here. It's been very nice so far. So I'm going to talk about the Boltzmann equation without angular cutoff. It's kind of funny that nowadays what you say is without angular cutoff, because what we're really doing is trying to study the Boltzmann equation as it was originally written down. But for some reason, for historical reasons, people made an assumption which simplified the model. That was the angular cutoff assumption, and now we are going to try and remove this assumption and figure out what we can say. So that's the basic theme. But okay, so we're going to give 3 talks. The first one is an introductory talk. It's an introduction to the mathematics of kinetic theory, the Boltzmann equation, and some physical intuition, and that'll be the first talk today. Then the second talk today will be a discussion of our main results establishing the global stability of the Boltzmann equation without this angular cutoff assumption for nearby equilibrium initial conditions, and we'll talk about some elements of the proof. And then in part 3, I'll discuss some recent proofs of optimal large time convergence rates to the equilibrium Maxwellians for collisional-kinetic equations. And the stuff from the second talk is a lot of joint works with my colleague Phil Gressman, and the stuff from the third talk is some joint works with Renjun Duan, who's here. Okay, so I noticed that you have Maxwell in a statue in the courtyard outside, and then I was hoping that you might also have Boltzmann, but I couldn't find him. But in any case, these are the heroes of what we're talking about, Boltzmann and Maxwell. And the overall theme that I want, if there's one message that I want to send to you, is that this Boltzmann equation, which was derived in the mid-18th century by these two guys, Boltzmann and Maxwell, is a physical, non-local, geometric, fractionally diffusive PDE. Now, if you're asking what does that mean, then it's a good thing to ask, because these guys, when they derived the equation, would have also asked what does that mean. The really amazing thing that I find about this equation is that it exhibits a mathematical phenomena that is really present in the physical model, but that was somehow way beyond the mathematical understanding that these guys possibly could have conceived when the equation was written down. So there's a phenomenon going on in this model that was yet to be discovered mathematically. It took basically 100 years after they wrote it down to really have the mathematical tools to see how this equation actually behaves. And explain that in more detail as we go on. But okay, so let's talk about physics a little bit. This first lecture is really going to be very introductory. So the Boltzmann equation was derived by Boltzmann in 1872 and Maxwell in 1866. And it models the behavior of a so-called dilute gas. Now you might ask, why are we calling this the Boltzmann equation if you're saying it was derived by Boltzmann 8 years or 6 years after Maxwell derived it? So why isn't it the Maxwell equation? There's good reasons for that, because Boltzmann really figured out a lot of things that Maxwell sort of left behind and didn't worry about. So he, for instance, this H-theorem that we'll see was mainly Boltzmann's discovery. But the Boltzmann equation models the behavior of a dilute gas. So you consider a gas as a large number of particles greater than or equal to 10 to the 23rd, which is a pretty big number. Approximately 10 cubic centimeter of a gas contains something like 10 to the 23rd particles, and they all obey Newtonian mechanics. So they all kind of are moving via a system of Newton's equations, and so each particle has its own position and velocity, and it travels in a straight line until it collides with another particle. And when two particles collide, they have some kind of a interaction that happens. And we only consider binary collisions, and that's not thought to be an extremely serious assumption because any collision with more than two particles would have to be instantaneous. So if two particles collide milliseconds after one another, then that's considered to be two consecutive binary collisions. It's not a triple or higher order collision. Okay, so collisions obey physical conservation laws of momentum and energy. And the Boltzmann equation is derived by taking a continuum Boltzmann-Grad limit, which we heard a little bit about in the morning in substance. The Boltzmann equation is probabilistic. It describes the evolution in time of an arbitrary particle in some ensemble of particles with a given initial position and momentum. And this is a remarkable historical fact. This is, as far as I know, the first evolutionary physical partial differential equation that was written down that modeled the evolution of a probability density function. And it was incredible because the major thing is that if you want to model a gas using Newton's equations, you have to write down 10 to the 23rd collections of Newton's equations, and you have to have some interaction potential that's modeling the interactions between particles. And in 1860, that was a daunting thing to do, and even in 2011, with all the modern computing power that we have, it's still a daunting thing to do. And so what you do instead is to write down an equation for a particle chosen at random from your ensemble and expect that that gives you good information. In fact, it does. Okay. So I stole this graph, and it doesn't look so good right now, but maybe we can fix that. Okay. So this is just an animated GIF of particles moving around and crashing into each other and bouncing off the walls of a box. And this is kind of a little image that I want to put in your head about how what we are thinking of. What?
What's red
They're, for our purposes, they're meaningless. I found this on the internet, and I didn't come up with it. Just to indicate different particles. Okay. So that's the picture that I want you to have. But yeah, we got that from Wikipedia. But so this is the Boltzmann equation. It is the time derivative of f, where f is your unknown, plus the velocity dotted with the spatial gradient of f is equal to this QFF thing, where QFF is a collision operator, and your x is in some domain which we're calling omega, and v is your velocities, and these are in the whole space. So x is position, v is velocity, and t is time. Time is going forward, and this capital F is a probability density function in position and velocity, and omega is some domain in space, and v dot grad x F is called the free transport term, because if you remove this Q, if you set this equal to 0, then you just have the particles freely moving and never crashing into each other. So that's why you think of it as free transport. But somehow free transport is corrected by this collision operator, QFF, which is the main theme of what we're talking about. So QFF is local in T and X, and it's a quadratic integral operator, which is something we'll talk about. And this, as we said, this is derived by Maxwell and Boltzmann. And okay, so the next thing I want to talk about is the physical conservation laws of energy and momentum. So given two particles with velocities v and v star, after these particles undergo a binary collision, they have outgoing velocities v prime and v prime star. And these collisions are supposed to obey the conservation laws of momentum and energy, which are written right here. So these are four equations. There's one energy equation for the modulus squared of each velocity, and then there's the momentum equation. So the sum of the momentums and the energies has to be conserved. And so up here there are 6 unknowns, and there are 4 equations. So that means there are 2 free parameters. And so the set of solutions to a collision can be parameterized by the sphere, S2, and you can solve these for these post-collisional velocities v prime and v prime star in terms of the pre-collisional velocities v and v star in several different ways. In this morning's talks we saw a different set of coordinates, but this is the one we'll use here. So these are the post-collisional velocities, and what you see here is that they sit on a sphere. So this is the sphere with center v plus v star over 2 and a diameter v minus v star. And so all of these velocities are moving around the sphere. And this is beautiful because it describes the aftermath of a binary collision probabilistically. So you have a whole collection of points on the sphere that are all the possible velocities that you can come up with after a binary collision. Okay, so now we're back to the Boltzmann equation up here, and we're ready to talk about the Boltzmann collision operator. So the Boltzmann collision operator is a function of velocity space. It's local in the t and x variables. It only acts upon the velocity variables in this equation. And so you can define q of fg. So you just think of these as different functions. As the integral over dv star, the integral over sigma of b of v minus v star comma sigma, and then you have these things here. So you have f prime star g prime minus f prime g. I said that wrong. But f prime star g prime minus f star g, and these are shorthands for the functions of the different variables. So g just means g of v, f star just means f of v star, g prime just means g of v prime, and f prime star just means f of v prime star. And so you have this cancellation going on here. And I'll just remind you what the pre-post collisional velocities look like. Okay, so one thing that I want to point out about this equation while it's up here on the board is that one of the highlights of Newtonian mechanics is that you can actually derive this equation completely rigorously from first principles of Newtonian mechanics, at least on a very, very short time interval or for very, very small initial data. Landford did that in 1975 for hard spheres. And this is one of the major examples of a success story of actually being able to derive an evolutionary partial differential equation from Newtonian mechanics in any situation. So it's really amazing in that sense. Okay, so what we're going to focus on now is this quantity here, which I haven't talked about at all, the so-called collision kernel, which is this function b. And that's going to be the theme of what we're talking about. So a complete description of the aftermath of collisions requires precise physics, but there are a few physical approaches. The first one is the hard sphere case, and in this case particles are assumed to be something like billiard balls, and they smash into each other and change velocities as a result of direct collisions. And the next situation, which is really what we're going to be focused on in this talk, are these so-called inverse power law interactions. And here the particles are assumed to interact pairwise through inverse power law potentials of the form r to the minus p plus 1 for some p bigger than 2. In this case, the preferred consequence of glancing or grazing collision, the preferred consequence is a glancing or grazing collision, and velocities only change a small amount as a result of these collisions. The velocities don't change very much. In some sense, particles don't even really collide. They just sort of interact at a distance and they graze off of each other. And the last case, which we won't talk about too much, is the Coulomb potential. So when P is actually equal to 2, something awful happens to the Boltzmann equation. And in fact, the Boltzmann equation becomes an ill-defined operator. And so you need, Landau came along in 1936, and he wrote down something called Landau's equation, which is the correction to Boltzmann equation for the important case of the Coulomb potential. But that's all I'm going to say about this in this talk. Okay, so the collision kernel B that is our main focus of this slide. And an amazing thing is that James Clerk Maxwell, whose statue is actually on the walkway outside, computed this collision kernel from a two-body interaction situation using this intermolecular potential 5r is equal to r minus p plus 1 for some p's between 2 and infinity. And he figured out that the kernel takes product form as arguments of b minus v star sigma is equal to v minus v star to the gamma in norm times the function lowercase v of cosine theta. For cosine theta is this angle between the relative velocities v minus v star and sigma. And so this is nice, and the reason, but it turns out that this function b is not expressible in terms of elementary functions. So it's a well-defined function, and you can derive it completely physically from this intermolecular repulsive potential, and you see it in standard physics books, this calculation that was actually written down in Maxwell's famous 1866 paper from the Royal Society. But this function b is well-defined, but it's not function that you can write down a formula for. But you can figure out exactly what its asymptotics are. You can see that how it behaves for all angles. So this angular singularity sigma is not locally integrable in the sense that sine of theta times v of cosine of theta behaves like theta to the minus 1 minus 2s as theta goes to 0. So this is a bounded function if theta is bounded away from 0, and as theta goes to 0, this function behaves, blows up like a power law. And this was known to Maxwell and Boltzmann. And the kinetic factor v minus v star to the gamma can be singular. So gamma is p minus 5 over p minus 1, and s is 1 over p minus 1. So s is between 0 and 1, and gamma is bigger than minus 3 for all values of p. And for our mathematical purposes, all we're going to do in this talk is worry about varying values of s and gamma. And so let me just stop for a second and say it's really amazing to me that you could see this model and that it was actually written down by Maxwell and Boltzmann in the 1860s and 1870s, and that they didn't just throw it away. Because this quantity up here is actually the difference of two infinities. So if you have this expression right here, which Maxwell and Boltzmann had, then the difference of these two terms is infinity minus infinity. And how do you make sense out of that? Well, in 1866, it was pretty hard to make sense out of that. But what Maxwell did, amazingly, is he came up with the notion of the weak formulation of an equation. So he integrated this quantity against the test function and performed a change of variables and realized that inner product that you got was finite. And he said, all right, great. So in a sense, he wrote down the weak formulation of the Boltzmann collision operator long before the notion of weak derivatives even really existed. So I'm told Riemann knew a little bit about weak derivatives before Maxwell. I doubt that Maxwell knew about what Riemann had done. And this was 50 years before Leray came along and really pioneered the notion of weak derivatives. So it's really amazing that we have this model, because it really does make sense, in spite of the fact that when it was originally written down, it may not have made so much sense to a lot of people. Okay, so this is the model that we want to study, but for a long time, this model was sort of thrown away. So in a famous paper by Harold Grad in 1963, he proposed that it makes sense to make this so-called angular cutoff assumption, where you assume something that's not true, in the sense that you assume that B is either in L infinity or B is in L1, which means that it does not blow up. And I think it's fair to say that the vast majority of research on the Boltzmann equation from the 60s to say the year 2000 made these assumptions, and these assumptions are not as widespread today, but they're still in widespread usage. And the theme that I want you to take away from this is that they're, in some sense, throwing away half of the model, and they're not really the greatest assumptions to be. Okay, and here's why. So cut-off versions of the Boltzmann equation, so if you make these assumptions up here, and cut-off versions of the Boltzmann equation are known to propagate singularities. And so you have these results: Boudin, Develet, Duan, Li, Yang, and Bernie, Develet, showing examples where the Boltzmann equation actually behaves like some kind of a wave equation, and it propagates singularities if you make these assumptions. And on the other hand, if you don't make these assumptions, the full Boltzmann equation without this cutoff assumption experiences smoothing effects. And these results go back to Lyons and Develet, and then Chen, Develet, he, and this team of Alexander, Morimoto, Yukai, Yu, and Yang have proven results showing that the Boltzmann equation exhibits a C-infinity smoothing effect, so it behaves like a heat-type equation. So there's a big difference between these two cases. Okay, and the one thing that we will show is that the full Boltzmann equation without cutoff near Maxwellian has better convergence properties. It decays as time goes to infinity, converges to equilibrium much faster than the cutoff Boltzmann equation. The non-cutoff is better than cutoff. Okay, so the next thing I want to point out is that so there's a lot of work on the Boltzmann equation, studying the cutoff Boltzmann equation, but there's not really so much work without cutoff. So there's basically what's on this slide, and I won't try to read it to you. But so there's a very limited number of results without cutoff, but there's a lot of results with cutoff. And so we're trying to change that. Okay. So, yes. Okay, so now there's an old conjecture regarding the angular singularity for the Boltzmann equation. So the Boltzmann collision operator without cutoff has been widely conjectured to behave as follows. So the mapping F going into Q, G of F, where G is thought of as some parameter function, is supposed to behave like a fractional Laplacian plus lower order term. So it's supposed to diffuse like a Laplacian operator to the power S, where S is between 0 and 1. And so the linear intuition for this conjecture has been credited to Carlos Giorgiani in his 1969 book about 40 years ago, because he computed the eigenfunctions of the linearized Boltzmann collision operator, and he observed that they behave like the eigenfunctions of the S power Laplacian when S is equal to a quarter. Okay, so the thing I want to point out is that this conjecture does not take the collisional geometry into account. This is a so-called isotropic flat Laplacian where there's no geometry involved, and this intuition is correct to the order of differentiation, and it's correct locally in a ball or something like that, but it's in fact wrong in the sense that there's geometry present. So the mapping F going into QGF really behaves like this bracket V, so V to the power gallon plus 2S times the Laplace to the P of S. So it's an S power Laplacian, but it's not an isotropic flat Laplacian. In fact, it's a metric Laplacian. So if R3, excuse me, so if R3 is identified with a paraboloid and R4 by means of the mapping V goes into V comma 1 half V squared, then the Laplace P is the metric Laplacian on the paraboloid induced by the Euclidean metric in R4. And this is really the way the Boltzmann collision operator behaves, and we can prove that. So if that was a little bit formulaic, hopefully this picture is a little bit illuminating, a little bit more illuminating. So what I want to say here is this is a little bit of a cartoon. It's not really 100% of a rigorous picture, but the idea is that if you start out with some kind of a bump near the origin, then a flat Laplacian, even to the s power, would just give you this bump right here in the middle as time goes forward. But if you start out with a little bump in the center and you operate on it by the parabolic Laplacian, by the fractional parabolic Laplacian, then you get these additional sort of crazy waves going on. So this is a computation that was done in Mathematica. But the idea is that it's not sort of isotropic diffusion that behaves in the same way in every direction. It's in fact diffusion that behaves in different ways in different directions, and that changes as you sort of move around velocity space. And so this is a picture. Okay, now I'll give this to you in the form of metric semi-norm. So the sharp fractional diffusive behavior is this space that we're calling ns gamma. And so we introduce a weighted geometric fractional semi-norm that we call ns gamma dot, where f ns gamma dot squared is equal to the integral over R3 of dv, and you have this bracket v to the gamma plus 2s plus 1, where then you integrate over dv prime, also over 3, but you restrict to this distance being less than 1. So you want dv v prime to be less than or equal to 1. Forgot that I never actually defined this quantity. Okay, and so there's this weight that's sitting here, and then there's this, you're restricting to the distance, this parabolic distance being less than or equal to 1, and then you're integrating over f of v prime minus f of v star squared divided by the distance v prime to 3 plus 2s. And we use this metric on this so-called lifted paraboloid because you're sort of lifting into a higher dimension and then restricting to the paraboloid in that dimension. So you have this distance is the square root of the normal Euclidean distance plus this extra v squared minus v prime squared term, and this is. So if you got rid of this term I'm highlighting here, then this would just be a standard isotropic flat fractional diffusion. But this extra term adds these non-isotropic effects that we'll explain more as time goes on. So our precise statement of the thing that I claimed on the previous slide is as follows. So if you let f squared of L2 gamma be the integral dv of gamma of f v squared, then what we proved with my collaborator Phil Gressman is that the L2 inner product of QGF comma f behaves like f squared of this ns gamma norm plus f and this L2 norm plus terms which are lower order in the sense that they do not differentiate. And we can prove that, so we think of the function g as a parameter, and we can prove the lower bounds assuming only g is an L log L intersect L1 on the ball of radius r centered at the origin, where r is whatever, some positive number, it doesn't really matter. And so these are really general assumptions, and this is pretty close to the best you can hope for, I think, in terms of the lower bound. So this shows what the diffusive behavior is in that sense. Okay, so this is really the thing that was amazing to me, is that these kinds of concepts and quantities were something that didn't come into people's mathematical imaginations until, I don't know, 50 years ago, which was maybe 100 years after Boltzmann and Maxwell wrote down their equation. It's kind of like it's amazing, this interaction between mathematics and physics, and how there's this kind of feedback loop where we can understand things using physics, and then we can understand physics better using mathematics. And, so that's that. All right. So where does this come from? So how do you see this in this operator? So I want to convince you that you can actually see this behavior that's on this slide in the Boltzmann collision operator. So we want to flatten the diffusive effects of the Boltzmann collision operator. This is an idea that came out of my study of special relativity in some sense. So if you define v prime bar to be a 4 vector, so you have v1 prime, v2 prime, v3 prime, v4 prime, and you similarly define v prime star bar and v star bar, and you consider v prime squared to be the square of the first 3 components, then you can identify R3 with R4. So you can the integral over R3 is the same as the integral over R4 times the delta function, where the 4th component is restricted to v prime squared over 2. And this is a Radon measure. And at this point, this is just a tautology. It's not really a meaningful statement, but as we go on, it gets more meaningful. So now we consider this measure d mu, where so you can write v bar as v norm v squared over 2, and then the integral d mu is defined to be the integral over R4 of dv prime bar, the integral over R4 of dv star, and the integral over R4 of dv prime star bar. So you've lifted everything up, and then you stick all these delta functions in here. So this first delta function is a 4 delta function because it has 4 variables in it, and it restricts you to the conservation laws that we talked about previously. And these other 3 delta functions just restrict you to this a mass shell, to this so that you're sitting on this paraboloid. And you can do this, and this is gives you an equivalent expression for the Boltzmann collision operator that you don't really see very often in modern day textbooks, but is sort of known to sort of physicists from 50 years ago, at least in special relativity. So you can write QFF as a function of v bar, so it's a function of both v and modulus of v squared, and then you can integrate the Boltzmann collision operator over d mu, and now you think of everything as being a function of these 1 higher dimensional variables. And somehow the major insight here is that you can stick yourself on this Newtonian mass shell. So normally when you think of a mass shell, you think of a special relativistic mass shell, but there's nothing logically preventing you from doing the same thing for the Newtonian case, where you don't have special relativity. And then you get this operator, and then this is the Boltzmann collision operator again. But now you can see this parabola just sitting everywhere in this equation. It's in all of these Radon measures. It's just plain for the eye to see. Okay. So the next thing I want to talk about is the conservation laws for the Boltzmann equation. So the conservation of mass, momentum, and energy hold formally as follows. So the integral over dx and dv of 1, where v or v squared about 15x and v is equal to the corresponding quantity initially. So the integral over dx and omega and dv and R3 is conserved, and so 1v and v squared is conserved. And the equilibrium states are Maxwellian, so even if Maxwell didn't get his name on the equation, at least he got his name on these Maxwellian equilibrium states. And so you can define mu of rho u and t to be rho over 2 pi t to the 3 over 2 times e to the v minus u squared over 2t, where rho is the so-called fluid density, u is the bulk velocity, and t is the temperature. And so you see here that there's a 5-parameter collection of equilibrium states. So there's a rho, t, and u to find 5 free parameters. And then up here there are 5 conservation laws. And so the 5 conservation laws and the 5-parameter Maxwellian imply that for any given initial condition there exists a unique equilibrium state that corresponds to that initial condition, and that's the one which has the same conservation laws as the equilibrium state initially. Okay, so the Boltzmann equation satisfies very, very weak a priori estimates. So the best you can hope for is that the integral from 0 to t of the integral over dt, dx, and dv of f multiplied by either 1 or v squared or x squared or the absolute value of log of f is bounded if the corresponding quantity is bounded initially. So if this quantity is bounded initially, then these bounds are propagated by the equation. And the reason why it's so hard to prove mathematical results for the Boltzmann equation is because this is sort of the best you get, and these spaces from a mathematical point of view are very, very weak, and they don't really give you a lot of information. But there's one more thing you can do. You can define this h functional, and so you can define h of t to be equal to negative integral dx, integral dv of f log f, and then you can formally differentiate this quantity and interchange derivative and integral, and you obtain the so-called famous Boltzmann H-theorem, which says that dh dt is equal to the integral over dx of d of f, and the entropy production functional is non-negative, and it's given by this quantity right here. So d of gf is equal to minus the integral dv of q of g of f log f. And this is, in some sense, the second law of thermodynamics. It's saying that entropy is increasing as time passes for the Boltzmann equation. Entropy is increasing, and the 140-year-old Boltzmann H-theorem, which was noticed by Boltzmann, not Maxwell, which is really why Boltzmann got the equation named after him, is that the same thing we wrote on the previous slide. The time derivative of the entropy is increasing, and entropy is maximized by the Maxwellian equilibrium state. So mu of rho u and t is equal to this quantity again. And so Boltzmann himself predicted that as a result of the H-theorem, solutions to the Boltzmann equation should converge to the corresponding Maxwellian equilibrium states as time goes to infinity. And you can do a formal calculation, and you still see in physics texts today that the solutions to the Boltzmann equation converge to equilibrium. And the proof is this formal calculation of taking the time derivative of the entropy, showing it was positive. But unfortunately, this proof was held back by what you might call slight analytical difficulties, because the calculations that the amount of regularity and integrability that you need in order to justify this calculation is unknown to be propagated by solutions to the equation, so you don't really have a proof. And so what we want to prove is this convergence to equilibrium. We want to prove global existence and uniqueness of solutions to the Boltzmann equation and asymptotic time convergence rates to equilibrium for the full Boltzmann equation. And so what I'm going to try and provide for you in the next talk is how we give a rigorous proof of this statement in the close to equilibrium context. So I think I'm ending 10 minutes early, but if you permit me to take a break now and then give me an extra 10 minutes for the second talk. Sure. Okay. So
this is the introduction part, right?
Yes.
the real talk. I think.
Yes.
The second talk. So do you have any questions and comments before the second talk? Yeah.
So when you say diffusion, is corresponding exactly which kind of diffusion ablation sort of be corresponding to that kind of distance?
Yes. So why am I calling this diffusion?
Yes, ablation is taking maybe.
So that probably corresponds to the operator who like fractional diffusion.
Yes. Yes, so this is a fractional diffusion to the power s.
It's Laplacian chapter.
Yes, to the power s. So this operator is essentially this in terms of L2 spaces. So you have to be very careful. So you can define the. So if you want to think about the Laplacian to the power s, what is this equal to? You can define it to be Cs integral dv star f of v f of v star over v star.
This is fractional derivative.
Yes. So in the isotropic case, you can define the fractional Laplacian this way, or you can define it in terms of the Fourier transform, right? You can. Gives you a well-defined way to define the fractional Laplacian, and this is a similar formula for defining it. But for these geometrical Laplacians, it's much harder to define. You have to resort to spectral theory, which I don't want to get into. But this is mainly using this expression is correct, at least in terms of L2 spaces. But I'm just doing it as a heuristic explanation. This is really what we're talking about, is this kind of space. So if you really carefully define this metric Laplacian, this fractional metric Laplacian in terms of using spectral theory of operators, then you can show that in L2, what I've written on the previous slide is equivalent to this.
Is there any relation between this kind of room for Boltzmann to Edna?
Yes. Oh, so I should say that. So this is completely consistent with the behavior of the Landau equation, although that was not known. But this is the same exact behavior. If you send S to 1, then this is the diffusive behavior of Landau. It's the same.
Any questions? Comments? So sort of the lifting up, right?
Yes.
That kind of idea is one of the crucial
Yes,
things.
I think so.
It seems to me, and so that reminds me of this, the algebraic geometry and the things in happening in algebraic geometry.
Yes.
Usually, singularity occurs in this process of projecting.
Yes.
Right? So in other words, lifting out on the other hand, that saves somehow the issue of this singularity. So probably looks to me this similar idea in your argument.
Yes. It sounds similar to the way you described it. That's not where it came from.
The algebra
From our point of
geometry,
view.
I mean, that in the brings back
Yeah.
like the algebra, the resolving singularity in the algebra geometry.
By lifting up. Yeah.
So-
No, I think lifting up is kind of like works kind of like magic here. It's sort of.
Right, so that's what they do here.
Yes.
So that seems to me that one of the crucial points.
Absolutely.
Methods, right?
Absolutely.
So- also, you said that it's related to the method in the GR, right? And the
Yes.
special relativity.
Yes. So it.
Exponential.
Yes. So these operators are rotationally invariant, and in
Right.
special relativity things are
Exactly.
Lorentz invariant, and you can write down a special relativistic Boltzmann equation. And the way you change variables in special relativity is to lift everything up to 4 dimensions and integrate over Radon measures and use 4-dimensional Lorentz transformations. And so that's sort of how I see this.
Right. So, of course, there, I mean, the time is somewhere.
Yes.
Yes. Here.
So for the Boltzmann equation, you have space-time Lorentz invariance, but you also have momentum Lorentz invariance.
Okay.
And so what I'm thinking of here is the momentum part of it.
Yeah, I think so. Good idea. Okay, so any other questions? Some of you are not familiar with this. Some of you are familiar with it anyway. So if there's not, then we can pick a break, right? And then maybe we can start 3.
Yeah.
It will be fine.
Yeah.
Okay, so we can start at 3 and so let's give thanks to speakers for very intensive, nice talk.